Hey, listeners of the Bio Report. Before we get started this week, I wanted to tell you about the digital library from Deep Dive. How much time does your team spend looking for research papers? Google, PubMed, social media. There's got to be a better way. You can now search a reference database of 100 million scientific papers and read the full text of 20 million articles, annotate them, and share with colleagues. It's the smarter way to do research. Here's the best part. If you're like me and been frustrated by not being able to access articles you find because they're behind a paywall, I've got good news. With Deep Dive, you get one-stop affordable research. If you're a listener of the Bio Report, you can try the enterprise version of the service for free for 1 month. Go to deepdive.com/podcast and enter the code BioReport. That's Deep Dive, DeepDive.com/podcast. And the code is BioReport, one word, all caps. I'm Daniel Levine, and this is the Bio Report. Hypoxia, a potentially fatal shortage of oxygen in tissues, is a complicating factor in a variety of serious illnesses, including cancer, cardiovascular disease, and respiratory conditions. Diffusion Pharmaceuticals' lead experimental candidate, TSC, enhances the ability of the body to deliver oxygen to where it is needed most. We spoke to Bob Cobuzzi, CEO of Diffusion Pharmaceuticals, about hypoxia, the company's lead therapeutic candidate to address it in a broad range of conditions, and its clinical development strategy for the drug. Bob, thanks for joining us.
Danny, it's a pleasure to be here. I really appreciate your invitation.
We're going to talk about hypoxia, Diffusion Pharmaceuticals, and its pipeline and a product strategy with its experimental therapy, TSC. Let's start with a little biology basics, though. What role does oxygen play in the body?
So, great question. Seems very fundamental, but I think it's one that gets overlooked most of the time through medicine. It's just taken for granted. So, air comes in. Ambient air is about 21% oxygen. That oxygen goes into the bloodstream through the lungs, hops on board the hemoglobin molecules within the red blood cells, and takes a ride to the areas of the body where it's needed. And what it does when it gets there is it's not just a gas floating around. The oxygen itself is responsible within the mitochondria, the powerhouse of the cell, for enabling the conversion of the sugars and the foodstuffs that we take into our body into energy. So that's its primary role. Without that, no energy, cells die. Life itself, as humans, mammals, most of biology doesn't exist as we know it.
And as red blood cells transport oxygen through the body, how does it get to where it needs to go?
So it's, again, one of these things that often gets overlooked. But in essence, what happens is, so the red blood cells are constantly circulating. They're on a track, if you will, in the form of the cardiovascular system, leaving through the heart, coming in through the lungs, into the heart, out into the circulatory system. They pass around through the body. And what happens is they deposit the oxygen at areas where there's a deficit. So oxygen, as it moves through the bloodstream or even moves through the body itself when it's not attached to the hemoglobin molecule, is always looking to move down a concentration gradient from the areas of high concentration to low concentration. So in a sense, trying to establish equilibrium. So for example, if you've been out for a long run, or you've done something that causes, under normal circumstances, your muscles to not have or to have used up all its energy and consequently all its oxygen. The oxygen is going to be, from what all of the research shows, more inclined, so to speak, to release at that point and enter through the bloodstream into the tissue to fulfill the deficit that exists.
So what is hypoxia?
So hypoxia is a reduced amount of oxygen. I won't say it's zero oxygen. It can be anything from a reduction in what would be normal oxygen states, the normal amount of oxygen present in the tissue, to virtually zero. So less oxygen than is needed to preserve the normal function of the tissue.
Hypoxia plays a role in a large number of health conditions. Is this an effective illness, or is this somehow central to the disease process?
Yeah, a little bit of the chicken and the egg there. Under most circumstances, hypoxia itself is going to be a result. So case in point, something that's near and dear to all of us at this point in time is the COVID situation. And with COVID, I think coming in a year plus ago to our understanding of the disease, and I think it'd be safe to say that science and medicine hasn't completely caught up with the biology of what's going on. There's still a lot of speculation, but the reason I raise it here is because hypoxia in those instances for patients who have severe forms of COVID, whether it's because they've got lungs that aren't taking oxygen up well enough, or they've got clots, which is now something we've seen occurs much more frequently amongst patients, particularly hospitalized patients who have severe forms of COVID. In those circumstances, you've got blockages that prevent adequate amounts of oxygen getting to the tissue. And so creates a hypoxic situation, results in tissue damage, and ultimately, unfortunately, in severe instances, can cause death. So
your lead experimental candidate is TSC. What is TSC and how does it work?
So TSC is trans-sodium crucetinate is what it stands for, the three initials. And crucetins, of which trans-sodium crucetinate is one, are derived from plant source, in this case from the spice saffron, which comes from a plant called Crocus sativus. It's a flower. It was identified by Dr. John Gaynor, one of the founders of the company, a number of years ago, as being a molecule of interest in some work he was doing with Navy at that point in time to look at a drug that could putatively be of value in treating hemorrhage, major blood loss that results in hypoxia, what we've been talking about here. And as a consequence, he identified this molecule, which had been around and observed for thousands of years as having important medicinal properties, but itself wasn't pharmaceutically acceptable as a form, meaning you couldn't easily take it and get sufficient concentrations taken up into the body to have the effects that were desired. So as a consequence, he made some changes to the chemistry and came up with TSC. And it works by actually causing a change in how the water molecules in the blood. So blood itself is about 50% plasma, and the plasma is about 90% water. So what TSC does is it causes a change in how the water molecules interact with each other so that they form more of a matrix structure. And that matrix allows, as I mentioned before, the oxygen to move from the areas of high concentration more readily to the areas of low concentration. Because otherwise, in normal circumstances, the water molecules are all just randomly moving about, and it physically creates a more tortured pathway for the oxygen to move along the gradient from high to low concentrations. So it facilitates the process by, in essence, opening up the water molecules a little bit within the bloodstream.
In cancer, TSC can play a slightly different role. What effect does reoxygenating treatment-resistant cancerous tissues have?
Yeah, so again, an excellent question. I wouldn't go so far as to say it plays a different role. So the mechanism is still the same, but what actually happens there, and there were some studies that were done before I joined the company a number of years ago looking at glioblastoma multiforme, which is a type of very lethal type of brain cancer. And the reason the drug was tested there is because glioblastoma tumors, like many other solid tumors, actually are very hypoxic. by nature. Pancreatic cancers are hypoxic tumors. A number of these solid tumors are very hypoxic. Anyway, the reason it was used is because the understanding is that radiotherapy or radiation therapy, part of the way that it works is by activating oxygen molecules, creating free radicals, and that in turn causes tissue damage. And if you've got a hypoxic tumor, you get less effectiveness of the radiotherapy. So the thought was, gosh, if we can use TSC, the properties that we described a moment ago, as a means to improve oxygenation of the tumor, we should improve the ability or the effectiveness of the radiotherapy. So that was the intent of what was being done.
What's the case for approaching disease by treating hypoxia? Is the idea that this would be used in combination with more targeted therapies for different conditions?
Yeah. So if you're looking at a disease, and let's stick with cancer for a moment here. So this would be an add-on therapy. TSC would be an add-on therapy to radiotherapy, which we just talked about. And subsequently, depending upon the type of cancer, so in the case of glioblastoma, which I already mentioned, there's a therapy that's been identified as standard of care today, which is several cycles of radiotherapy, which are in turn followed by multiple cycles of radiotherapy combined with a form of chemotherapy. In this case, a drug called temozolomide is commonly used. And what happens there is you're using the TSC as a way of improving the effectiveness of both of those therapies. So in a sense, it's an adjuvant. Similarly, in the stroke studies that had been started before the pandemic, the intent was to improve the ability of the small amount of oxygen that is getting past the clot. In the case of an ischemic clot, where there's a blockage of the vasculature within the brain, to improve the oxygen. But to get rid of the clot itself, you either have to go in and physically remove the clot, which can be done surgically, or break the clot down with an agent called tissue plasminogen activator, or TPA. So whether it's the cancer cells, the tumor, or whether it's stroke or some other indication, the assumption is that we would be using this to improve oxygenation, but not necessarily to improve the underlying disease. That's not what this is being done. It's the oxygenation that's the target.
What's known about TSC from studies to date?
To date, what's been done is there's, over the past 20 years, been a tremendous amount of work done by Dr. Gaynor and the folks with whom he's worked, looking at the preclinical effects of this. So it's been well characterized in brain cancer models, as we discussed. Very interesting study showing, and I particularly like this because it's very graphic in a good way, of showing that if you take an animal that has a tumor, and the tumor itself, in this case, it's a glioma, again, like a glioblastoma type of brain cancer, and that tumor itself can be imaged using a technology called positron emission tomography. When you use that technology, you can light it up and it shows with the right chemical that you've got hypoxic tissue, that the tumor itself is hypoxic, and you add the TSC to it and the hypoxia goes away. I mean, it's a very graphic representation. Humans are not rats, but nonetheless, it's a very graphic representation. So like that rat model, we've got data in brain cancer, we've got stroke data. There's data also that's been obtained in a lung obstruction model. And then there's the human studies. We've exposed more than 200 humans to the drug over the years in clinical trials. The reason I say it that way and not patients is the original study that was done, which is typical for any drug development program, was in normal healthy volunteers. And after that, there were studies done in patients with peripheral artery disease, patients with glioblastomas we've talked about. A stroke study was started, and most recently a study was completed, 24 patients who had COVID-19. But I joined last September, and what myself and the new chief medical officer we're particularly excited about is a series of 3 studies, and I won't go into too many details here right now, but that are intended to look and demonstrate definitively the TSC can improve oxygenation in humans. Seems like a bit of a sidestep, But we think absent these data, we don't necessarily know the dose that we'd take if we wanted to go back and do, for example, the glioblastoma trial. So we think these studies are really, really important from a scientific standpoint to demonstrate the benefits of TSC in a human and make that the departure point for more definitive studies that look at clinical outcomes. So a lot of words, hopefully it answered your question, but I'm excited about this. And I think these studies that we're doing now are really going to give us some pretty significant data. So I think it's a key inflection point for us as a company.
Well, one of the challenges I always see for smaller companies to deal with when they have a product with such broad potential is prioritizing indications. How are you going about doing that?
Yeah, it's a very astute question. Second time today I've had a conversation like that, not in a podcast though. There's a couple of things. So breaking it down into pieces. Number one, the route of administration of TSC right now is limited to intravenous. So the drug today is formulated pretty simply. It's a sterile product that can be introduced directly into the bloodstream. And so that automatically limits, you're not going to give intravenous administered drug of any sort on a daily basis for outpatient therapy. So that knocks out a lot of the outpatient indications. You're really looking at hospitalized patients or people in special treatment areas where a skilled medical practitioner can deliver the drug. So that's point one. Point two is the amount of so-called pharmacokinetic data, the data that tells us what happens to the drug when it's administered into the body. Until the COVID study was conducted, we only had single dose data available to us. We didn't have repeat dosing. So something that, for example, would require prolonged exposure to this drug wasn't possible until such data were obtained. We still don't have what's called continuous IV infusion data. So the point being with all of this is the form through which the drug or the route of administration limits what we would look at for indications by itself. And then within that, because we are a small company, it's very hard to say we're going to go off and we're going to test ourselves in 6 different areas. So we're oftentimes going to look for the smaller indications that would allow us to have a smaller population of patients. Studies themselves are extremely expensive. And the other thing we want are studies that have very well-defined endpoints that allow us to measure without having to itself define whether or not the endpoint itself is valid for the therapy area. And unfortunately, there are still instances where that occurs. So we're choosing where it's IV, where we can readily use it to treat a very defined population of patients with well-known endpoints, and hopefully a small population where we can get a very quick readout on the study. So a lot of considerations that go into this matrix for the decision.
You also have a second molecule in development, DFN 529. This is in development for glioblastoma multiforme, or GBM. What is GBM and what treatment options exist today?
Yeah, so GBM, as we talked about a little while ago, glioblastoma multiforme is a very lethal form of brain cancer. It is very heterogeneous in terms of the types of cells. So it's not just all one type of cancer cell that exists necessarily. Forms obviously in the brain. It's a brain tumor in the cerebellar region. So the big white matter component of the brain. And what's important about this indication specifically is there are very few approved therapies for it. So as I was describing before, radiotherapy is almost universally used at the outset, and it's usually followed by the drug temozolomide. There have been other attempts to develop drugs through the years. Most of them haven't been terribly successful, or at least haven't improved outcomes dramatically or the survival time. Average survival, unfortunately, with this is 12 to 18 months. So limited options. One of the things that does matter is whether or not you have what's called a resectable tumor, one where as much of the tumor as possible can be surgically removed. And in the case of glioblastoma, if you can take the tumor, you're going to be much further out on the survival curve, so to speak. Your prognosis for a longer survival is better. Whereas if you have a non-resectable tumor, because it's too close to a vital part of the brain, then unfortunately the radiotherapy and the subsequent chemotherapy are not typically as effective. It doesn't mean there aren't exceptions. Oftentimes there are exceptions, but on average, it's not as effective. So limited in terms of the options there. And so anything we can do, including the addition of TSC that might improve the outcomes for these patients, even if it's just to improve the duration of time marginally, is considered a benefit.
Well, what is DFN 529 and how does it work?
So DFN 529 is a small molecule. It works by three fairly complex pharmacologies. So it hits multiple points, AKT, and I'm going to fail on the acronyms here. Even as a biochemist, I'm going to not remember all the acronyms. It would take a while to explain all of them. But for the three different points that it hits, it's not just GBM that it uses. What it's doing, in effect, is it's reducing the amount of new blood vessels that are growing in. So in addition to GBM, one of the places that DFN's been studied is in macular degeneration. And oftentimes what happens there is you've got an increase in the number of blood vessels that show up in the macula in the eye and cause a lot of problems and ultimately degeneration. And so in this case, what's happening is this drug goes in, and much like what's called a VEGF inhibitor, which get used fairly frequently now, actually inhibits the development of the blood vessels and over time has a benefit on the tumor itself, because it doesn't remain viable if it doesn't get a blood supply like other cells in the body.
It's actually inhibiting multiple kinases, I take it.
That's exactly correct. Yeah, AKT, PI3 kinase, yes, 3 kinases in total.
So is it like a combination therapy in one?
Yeah, of a sort. I think that's one of the things that makes it a bit complicated to explain, from the standpoint that as soon as you say that there's 3 different mechanisms, it sounds like it's 3 different drugs doing 3 different things, when in reality, you oftentimes have a primary biological target for a drug, and then you have what's called off-target effects. In this case, there's 3 primary targets, or 3 kinases, as you pointed out, that are affected by 529.
So the combination could be quite powerful, but I guess the concern is having off-target effects. What's known about the safety and efficacy of it to date?
So most of the work that's been done, there's paper published relatively recently, a couple of years ago, by an Italian investigator who looked and he saw beneficial effects of the drugs when it was evaluated in a glioblastoma model. And obviously exciting data. Well before my time and even before the 2 companies merged, the drug itself was picked up by Diffusion through merger with a company called Restrogenics, which had been developing the compound for a number of years before the merger took place in 2016. And on taking that over, some of the ophthalmic work had been done to date. And there were some pretty exciting indications that showed that there were effects in at least the early stage animal models that were done. Similarly, for the glioblastoma data that I mentioned from the Italian investigator, those were animal models as well. So there is some early efficacy data, but it hasn't been pushed so far, certainly nowhere near to the length that we have with TSC, that we have a complete portfolio of preclinical and clinical or early clinical data at this point in time. We just don't have that level of data yet. It's far behind as far as the development is concerned.
How far will existing financing take you, and what's the plan to fund operations going forward?
So we recently were very fortunate. We were able to raise capital through a financing back in February. And so we're excited to have, as we said in the 10K that we put out, our annual report not too long ago, that we've got financing available now through the end of 2023. And that includes the studies that we currently have planned, these 3 oxygenation studies, as I described them before, and also for what would be phase 2 clinical outcome studies that we're working on identifying. You asked about indications, is we choose the indications that we're going to pursue. So we're funded through those right now. It's exciting for us to have that kind of money. As a small company, you can often find yourself being hand to mouth. So we're in a fortunate place right now, but we have to be good stewards of it. We're trying to make sure that we're asking the right experimental questions and trying to get the very most from all the data that we're accumulating through the studies we're executing.
Robert Cobuzzi, CEO of Diffusion Pharmaceuticals. Bob, thanks so much for your time today.
Danny, it's been an absolute pleasure. I really appreciate your time as well. So thank you.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.